I don't know much.
But you kind of counted the Russians.
Yeah.
You know,
All right, folks, thanks for coming up. We have a forum. Still waiting on one committee member, but I think we have enough committee members. So it's a real pleasure to introduce Menachem Stern, or as we have come to call him, Naki. And I'd also want to give a shout out to Naki's dad, who's here.
Hello, everybody.
Naki's partner, Shahar. And whether you're aware or not, you're all being streamed live, or at least your voices are, to all over Israel, from what I understand.
All over the world.
All over the world. So Naki was the first graduate student to join my group about 3.5 years ago, and he didn't want to work on biology, and he wanted to work on mechanics, even though I had never worked on mechanics before. But as you'll see, he sort of managed to somehow combine mechanics with some ideas from biology, at least neuroscience. And depending on how things go today, he's hoping to start a postdoc. A postdoc at Penn, sort of continuing this unique line of work where he's going to work with Andrea. He hopes to work with Andrea Liu, who's a soft matter physicist, and Vijay Balasubramaniam, who's a physicist who works on neuroscience.
String theory. String theory used to be string theory.
Well, I think that goes without saying, right?
He's still maintaining it as a hobby. Thank you, Alvin. Thank you all for joining us today. I'd like to talk about some of the recent work we did in mechanical systems, specifically about learning in mechanical systems, or analogs to learning in mechanical systems. I'm going to compare them to the more traditional ways of designing these mechanical systems to do all kinds of interesting things. So let me start by introducing the terms, because design and learning mean different things to different people. So the definitions that I'm going to use are as follows. So engineered systems, you can look all around you, everything except the people is designed, meaning that it was rationally made to perform a certain task. So here are a few examples that we are all familiar with. On the other hand, there are evolving systems. These are systems that can change in response to external inputs, so things like natural or artificial neural networks. And these things, we say that they can learn. And the definitions that I'm going to use are from the dictionary. So design, by design I mean to create something according to a plan, while learning is to gain some knowledge or skill by experience. The experience or the example is crucial for learning. All right. So we're going to talk about mechanical systems today, complex mechanical systems, and I'm going to give 2 examples. These are elastic networks or networks of balls and springs, and thin sheets or origami. The reason I call these systems complex is because of this picture. If you look at the energy of different configurations of these systems, you will usually find this kind of picture. It's what we call a glassy landscape in the physics jargon. It has a lot of interesting features. It has a lot of minima and many stable states. It can do a lot of things. And both design and learning, the goal is to sculpt this landscape, change it, so that it fits some particular goal that we have in mind. And this modification of the landscape, this sculpting, is done by changing the parameters of the networks that they show here, which for the elastic networks is going to be the parameters of the springs, while in origami it's going to be the parameters of the paper, or ellipses, and so forth. And I'm going to talk about the differences between design and learning frameworks. I try to argue that learning has particular advantages that are worthwhile to make use of. And here's a short overview of the problems that I'm going to approach today. So here's the one-dimensional version of the glassy landscape I showed you before. This is just a generic landscape of a random network. And I'm going to ask several questions. can we design, in some sense, many stable states in a single system? Design meaning that we make these things rationally, choose these minima. If we can we do this by example? Can we sort of learn these features in the landscape? And if we can do those things, maybe we can go a step further and teach the system to classify inputs, meaning not only to have this landscape, but to associate different minima of the landscape with different classes of examples. Here are a few nice pictures. So let's start with multi-stability. And this is the idea that you can encode minima, stable minima in your landscape, and stable minima are supposed to be in specific places that you like. And these appear everywhere in systems, both in engineered and in evolving systems. Multi-stability is everywhere, so it's an important problem, and we'd like to be able to do the same thing in mechanics. So here's the goal. We want to make a material, in this case an elastic network, with multiple reserved stable states. So the network has a particular shape, which is specified by the locations of all the nodes, and each one of those shapes corresponds to some minimum in the landscape. How do we do this? We'd like to use two paradigms. One of them will be simultaneous design, in which we tell the computer what are all the desired shapes that we want, these three. The computer chooses the swings for us, and we get a design network. A different paradigm would be by continual learning. So here we shape the network in a particular shape that we like, and the network changes to accommodate this shape. And it can do this again and again, sequentially, while retaining the old ones. So it doesn't forget the things that it already saw before. In this sense, it's a way of continual learning, which already gives you a possible advantage of learning. This is not possible to do by design. Usually when you try to design stable states in the network, if you want to add another one, you have to redesign the entire thing. And this is something that I'm going to show that you can do with learning quite naturally.
Sorry, but what's the hardware that implements this learning?
I'll speak about it. This is the model that we use. But we'll first start with design. So how do we design stable states in the system? Let's say if you want to encode these particular stable states. So this is where the nodes are. There are 6 nodes in the system. And we want these 2 states to be stable. The algorithm goes like this. We just put the nodes in space. We connect some random strings between them. Then we ask the computer, we ask the Oracle what kind of springs do we need. The computer tells us. And then we just use these springs, and we can show that these 2 states are stable indeed. Of course, I didn't tell you how I did it, so let's go to the next slide. The point is, which is a little bit surprising, is that even if your springs are Hookean, linear, plain springs, the energy landscape is multi-stable to begin with. So here is a cut of the energy landscape of a random spring network. And there are plenty of minima. I just show a few of them. There are plenty of minima in the system. It actually scales with the size of the system. And the idea is that we can use these minima as a resource. We can move them around by choosing the right springs so that the minima are at the places that we want to stabilize. How do we do that? It's actually not that difficult. So here's the spring network that we have. The energy is just a sum over the energy of all the springs. These are Hookean springs that we all know. They have a stiffness and a rest length. R is the distance between the different nodes. And what we do is we take the derivative of this energy at the place we want to stabilize, at the state we want to stabilize, and we get a force balance equation. We know that if the forces at that point are 0, well, we know it's an extremum. We also have to verify that it's a stable point, but we can start with this. This is an ugly equation, so I'll just write it. I'll hide all the ugliness. It's basically a set of linear equations that one can solve on a computer for these parameters K and L, which are the parameters of the spring. And design would be solving this system. As I said, we also have to make sure it's stable, but this can be done. So this is what I mean. This is one idea that how to design multi-stability in an elastic network. How about learning? So this is already quite a weird question. What can a physical system learn? So I'm going to argue, first of all, that the physical system is usually stupid. It doesn't know that much. It cannot see or hear anything. But what you can expect the physical system to do is you can expect it to have a response to the particular state that it's in right now, meaning that you can write some sort of an equation for the parameters of the system P that they change in time as a function of the state they are currently seeing. And if you think about it, this forms a cycle, meaning that you might start with a physical state that looks like this. The parameters of the springs, let's say, start to change according to this equation, whatever this is. And then the energy landscape changes, so the physics, again, minimizes the energy. We get a different state. So this is the cycle of learning. Does this actually happen in physical systems? We know that it does. Specifically, we know that it does for neurons in the brain. There's this mantra of neuroscience that if two neurons are responding to some sort of an external input, at the same time, they tend to connect, to have stronger connections between them. So this is a natural sort of learning rule. And more recently, in the Nagel lab, lady who's sitting right here, has shown that you can age materials under strain to change the properties of different bonds and make them respond in all kinds of neat ways. So this is the flavor of the learning rules that I'm going to talk about today. But these are things that it's important to say that these are not weird imaginary rules. These are things that physical systems can indeed do, even simple systems like the one I'm going to talk about. So what is the specific learning rule that we have for multi-stability and elastic networks? Let's say we start with state one. It's going to be a sequential thing. It's state in its order. So we reshape the network into the desired state. Then we have some connection distance R. It can be arbitrary. And we connect every node in this, every two nodes in this circle by a unstrained bond. We do this for all of the particles, and because the bonds are unstrained, this thing is stable by construction. But now we have the second state, so we reshape the network again into the second state. The caveat being that we keep all of the springs that we had before. And for the second state, we draw new springs between the nodes. These are the orange springs, and they are unstrained in this state. But now, what about the blue springs? The blue springs that stayed from before are strained in this second state. So they are fighting each other. And the question is whether by doing this, we can stabilize more than one state. Can this actually be done in a real physical system? The answer is yes. So there is this example of DNA nanotubes that you can see in some specific places in space, and you wait a while and they just join up, forming a spring, something like a spring between them, and you can just do this. If you have a spring, if you have a seed with multiple heads, you can do it maybe more than once. And the learning rule that we actually get is very similar to what we use. So this is a physically motivated learning rule. Does it work still? It turns out that if you use regular Hookean springs, it doesn't work. This is the cut of the energy landscape that we get if we try to encode two states with linear springs. Stars denote the places that we want to stabilize, but we see that the actual minimum is around here. So the two states become stabilized. Okay, but let's not despair just yet. Mm-hmm. What if we use nonlinear springs? Nonlinear being that instead of using this power here, 2, to be 2 as before, I'm going to take a smaller number, let's say between 0 and 2. And it turns out that if you use this psi less than 1, you can stabilize more than one state. So this is, here I chose psi to be 0.5, and you see that there are two minima in the system, at least two minima in there, where we want them to be. That's the start.
Do you need the nonlinearity to be they're in the absence of a quadratic term, or can you have the ordinary linear spring plus a piece that is non-linear?
That's what we actually do. We have a linear spring close to zero strain, but then so it looks like this. Here,
So it's
here
quadratic.
it's rounded, but away from it, it's flattened like this.
So this is generic behavior material.
Right, it's not,
It's not an essentially non-linear bomb.
yeah, and there's no cusp here. It's not like, and it turns out that there's actually a transition at psi equal to 1. If you look at all the examples we have for larger psi, you see that the minima are not at 0 and 1, there are other places. But if you use smaller psi, the minima is stabilized where we want them to be. And to think about how it works, or why it works, we actually draw inspiration from sparse regression in statistics. The idea is that we want to minimize some function that looks like this, where we have an external force and the force due to the springs. Let's say that we just have two of them, 1 and 2. So it's well known in statistics that if you use this power to be 2, then this energy or whatever this function is minimized at some point here, which is just because the contours of this term are curved. So the minimum is going to be here, which is just a generic point. You see that you can have all of the terms contributing, all of the S's in this case. But if you use this sort of power, which is a 1 norm, the contours of the springs become cusp. And when you try to see where this is minimized, there's actually transitions. It's almost never minimized at some generic point. It always is minimized at the cusps because of where the intersections are generally between the cusp shape and the straight line. And this is actually what we see. So if we take linear springs, psi equal to 2, you see that the contours due to the springs are curved, and the intersections with the external energy is at some point where all of the strains are active, so all the springs are strained. On the other hand, if you take smaller psi, then the contours are cusped, and the intersections are always at the cusp. And the cusps have a nice property in which only one of those springs are strained. So in this case, only S1 is finite and S2 isn't. And you can look at histograms of the strains, and you can see that they are indeed have these sparse properties. If you choose small psi, you have this bimodal distribution with a lot of springs at zero strain. And this is exactly what we wanted to think about it, because we seeded this system, we built this system, but in the right state, there are a bunch of springs that are unstrained. So this is indeed the minima that we get in the network.
So S is just delta X.
S is delta X, yes.
So delta X will have a quadratic part plus the other one that is like this.
But this is what you see far away from S equal to 0.
Yeah, because there's
So,
see, the squiggle is less than 2. So the quadratic part should dominate over something that goes like 1/2.
so this doesn't make the parabola in the middle.
We can
It's
talk about
implicit there, right?
we can talk about the specific form later, but it basically looks like
The quadratic potential exists everywhere.
no, the quadratic potential exists only in the middle. Far away, it looks like S to the side.
So one thing I'm trying to understand is this S is delta X. S is delta X, right?
Yes,
It's the elongation. So this curve is delta X squared plus delta X to some power squared.
it's not like that. It's S squared in the middle, but then it transitions to something that goes like
I see.
non-linear thing.
I see.
Piecewise-ish, kind of interpolated.
It's a smooth transition. We can talk about it.
And what type of thing does that in mechanics? Because I mean, I certainly know a lot of things, but when I Taylor expand that delta X squared plus delta X cubed.
Yes, there are systems that work like this. Specifically, actomyosin has this type of potential. You can also make origami springs, things like this. So this is not like a completely weird thing, at least over some language. All right, so let me compare learning and design for this particular problem. So we have this simultaneous design where we just put everything on the computer. We get a desired network. On the other hand, we can use this idea of continuous learning, and then we get a completely different network. It turns out that you can actually find an optimum, in some sense, what are the optimal networks for this particular idea that I showed you. And if you look at the design networks, they are optimal for something that looks like a linear spring, more or less. And the learning networks really need strong nonlinearity. So these two things are very different. What might be the applications of such a system? So here's an example of robots that go around in circles and they create these shapes. And it motivated us because, in some sense, these robots also only know about one shape at a time. So we wanted to see if we can do something like this with our system. So here are my implementation of these shapes, and they have 35 nodes. They are fully connected. So indeed, if we use these nonlinear springs, we can stabilize all of them at the same time, and we can also move between them because all of them are encoded in the same system. It's just one network. So we can start, let's say, in the random state, and by applying the right forces, we can move between the three states. So this is more like the simple application for this kind of system. But let me go a bit further. So this system is essentially a mechanical version of Hopfield networks. So maybe we can do pattern recognition, like Flavius. So this is handwritten digits data set, MNIST, which is well known at this point. And what we can try to do is encode a state that we can name state 0 arbitrarily. And what they do is just pick a bunch of these zeros from the data set, and they take their average, and they say, okay, this is a state. I'm encoding it in the network with some topology that has 400 particles. Then I can do the same for a bunch of these digits, and we call it state 1. And then what I do is I initialize the system. I put it in some state which has nothing to do with the states that it used to learn. Let's say that we put it in this state. And if I used nonlinear springs, this guy relaxes here. And we sort of see that this thing is in the same family as this thing. Well, if I try to do it with linear springs, I don't know what it is. It also works with the 1. So this is, again, the same network. I showed it this thing, it went here. I showed it this thing, it went here. So this, in some sense, can do pattern recognition. We can go to even larger systems and do some face recognition with 10,000 particles. So these are the two states that I try to encode. I give the system a noise version of these states, and I see where it goes. So again, if you use nonlinear springs, you can tell that this guy is the cousin of this guy, and so forth.
What exactly? So just explain the algorithm. What exactly are you doing here?
Okay, so what I take the pixels of here, or the pixel values, and these I encode as particle positions in space. This is what the network is, and I connect it with strings according to the algorithm that I showed. And then it just gets this as a stable state, and this is a stable state. So this is in the machine learning chart when it's called unsupervised learning, because we did show with examples, but we didn't label this thing. So there's no particular state 0 or state 1 or states belonging to these people. These are just unlabeled minima in the landscape. So the next question that one might ask is whether we can do supervised learning, whether we can actually classify data. And this is a well-known problem in statistics and machine learning. You want to distinguish labeled classes in data. So you start with some continuous distribution, and you want to get a discrete answer. In this case, cat versus dog. And the most important things about this problem are these two. We want, first of all, to learn by example. We don't want to tell the system what a cat and a dog is. We want it to figure it out by itself. And maybe more importantly, we want the systems to generalize. We want it to predict the right class for examples that will not use during training. In practice, this is usually done with fancy machine learning techniques like deep learning. I'm going to do something a little bit simpler, but you can imagine that this sort of problem has many applications, and it's really worth quite a bit. And what I'm going to do is I'm going to try to solve this problem, or to do classification using thin sheets, using origami. And the idea is the following. Let's take some random sheet that looks like this, and we show it cats and dogs, and then it falls to something. I'm going to explain what I mean with that. The idea is the following. Each one of these pictures of cats and dogs correspond to some forces that we can apply on the sheet. So let's imagine that there are these rods sitting on the sheet, and the value of the force of each rod may be determined by the value of some pixel in this picture. So you can think of a representation that takes you from these pictures of cats and dogs to some forces on a thin sheet. So we want to train this system that starts with many, many folded states and some random classification that has nothing to do with the classes that you want to classify. And after you train it, you want all the cats to go into one particular shape, all the dogs to go into a different particular shape, but not only for the training examples, you also want to show it different things that were not shown during training, and you want them to go to the right place too. So first of all, let me give you the crash course for origami that no one asks for, but it's essential, still essential for this talk. So what is self-folding origami? It's basically a thin sheet, it has crystals on it, and it has particular smooth folding motions and things like this. These folding motions require very little energy input. And people know more or less how to make these things, at least what's the right topology of the crystals. And it's very useful for engineering because you can imagine that you make something in 2D and then you actuate it and it pops to 3D, which is very useful. And because it's everything is determined, the folding motion is determined by the geometry, you can do it over many lengths. And it's also a nice example. So this guy is the atom of self-folding origami. It's called the 4 vertex. It has 4 crystals attached to the vertex. This is when it's laid out flat. The value of each folding angle is given the name rho. And it turns out that even that this is 1 degree of freedom structure, it can fold. It folds smoothly as a 1 degree of freedom motion. It actually has two ways to fold. It's kind of unintuitive, but it can be shown. And if you look at the Reynolds landscape of this guy, then if you put it at the flat state, there are 2 folding modes that connect there. So if you want to go between this shape to this shape, you have to go through the flat state, but you can actuate both. And this is actually an issue. Why? Because if you go to larger patterns like this, in some sense, each one of the vertices remembers that it can fold into states. And the number of folded states available to this structure is much larger. So this is a glassy landscape for the folding of this particular pattern. The number of folded states that are available grows exponentially with the number of vertices in the sheet. You actually know this because you probably tried to refold the paper map. Once unfolded it, this is my example. So it turns out that this fold is actually NP-hard. You have to be very careful, exponentially careful in how you actuate the sheet in order to get the right folding mode. So for engineering, you may imagine that this is a major issue, and it isn't. But can we use it as a feature instead? So we have a project that basically talks about how do you rescue self-folding in this sheet. And it turns out that if you have sheets with homogeneous stiffness, the landscape looks like this. You have to be very careful about where you push the ball, because let's say if you want to get it into this particular valley, you have to put it at a flat state just here because it rolls down here. If you're not careful enough and you put it around here, you will fall into the wrong shape. This is some representation of the landscape. But it turns out that if you put heterogeneous stiffness, so different creases can have different stiffness, the topology of the landscape changes. So far away from the flood state, it still looks pretty much the same, but close to the flood state, all of the minima coalesce into one. So if you have this topology, it really doesn't matter how you illustrate it, you can only go in this path. And this is basically done by choosing the right planes. So can we use this mechanism to do supervised learning? Here's the problem. We have a force distribution, or two force distributions in blue or orange. You can call them cat and dog if you wish. And we want the sheet to be able to classify forces, whether they are blue or orange. So what we do is we just sample a bunch of them. These are going to be the training sets. These are the forces that are going to train the sheet. And we're going to enforce a learning rule that encourages the right folding and discourages wrong folding. What is it going to look like? So we start with a homogeneous sheet with the same stiffness everywhere. And we pick some two references for cats and dogs. The reference can be chosen by, let's say, the mean of the folding of all of the training examples. So in some cases, we can do once and for all at the beginning of the training. And then we show this origami a picture of a cat. We fold it and it folds into this. And we compare it to the cat reference. If it's close enough to the cat reference, we say, okay, there's a supervisor that makes the sheet softer. And it gets softer proportionally to the amount of folding. If you think about it, this kind of learning will reinforce the right folding. It makes it more likely that the same force will fold into the same shape. And we can do the same thing with the dog picture and use the same learning rule. And if we have the wrong shape, if we put it a cat picture and it doesn't compare to the reference, instead of softening it, we stiffen the creases. And then we get some heterogeneous stiffness at the end. This is again something that can be done with actual materials. Okay, does it work? If we start with this homogeneous sheet, it's not a very good classifier. So here are the forces that I show it, and it goes to 1 million colors, which means that it doesn't really classify anything. We just want it to be blue and orange. So we start training a little bit. Epoch is just the time it takes to show all the training example once. And after a while, let's say after about 40 epochs of training, we get this picture, which is pretty similar to this. Most of the forces around here fold into something that we call a blue shape. Most of the forces here fold into an orange shape. And you can measure this by looking at the accuracy. What's the fraction of forces that go into the right shape? And it goes up considerably, and it peaks at some point. So, and what I want to draw your attention to, that it doesn't work only on the training examples. It works also on test examples that were not part of the training. And this is a high-dimensional problem in some sense. If you look at where it fails, you see that it's close to the middle of the distribution. It does pretty well. The accuracy is very high. Close to the decision boundary that you want, it does much less so, which sort of makes sense. So how does it compare to learning algorithms? It turns out that all learning algorithms have very general properties. For example, if you compare the training error and test error as a function of the number of training examples that you show, you see this generic behavior. You see that the training error and the test error are not the same. If you have just a small data set, the training error will be low, the test error will be high. So the algorithm can remember what you showed it, it cannot generalize. And we actually see exactly the same thing, just that this is flipped because it's accuracy and not error. But you see that at low at low amounts of data, the training accuracy is high, test accuracy is low. And if you go higher, they become similar. So you can think about it, and this really compares in an interesting way to a lot of ideas in physics, where we a lot of times want to live in this regime, where we want to make materials that have memory to them. And in this case, memory means that you can know exactly, you can recover exactly the training set. If you show it an example, you can get it again. But you see that we get from learning, we learn that there's actually a trade-off between memory and generalization. So depending on what we want to get, we might want to choose the number of training examples that we have or that we use. How about real data? I just showed you a concocted distribution that you might argue that it looks like nothing. So I can classify this weird distribution maybe, but can I classify real data? So here's a classic data set with iris flowers. And there are two types of flowers. Both of them are irises. You will get given, in addition to the labels, 4 measurements, which are the width and length of some features of the flower. I'm not a botanist, so I'm not an expert in this, but these are pretty pictures. It changes name. It's not. It doesn't have this name anymore. But it's really interesting.
36.
So this is an old data set. And the data looks like this. The data looks like this. If you lay it out on some dimensions of the data of the problem, you see that the Phlogenica flowers sit around here, the versicolor flowers sit around here. There are some. It's not completely clear. It's not a clear linear distinguishing line. Can we learn this distribution? So we choose a bunch of flowers from this data set to be the training set, and these are the diamonds here. We start with an untrained homogeneous sheet. It doesn't classify anything, so we get a lot of colors here. It just goes into different forms of shapes. But as you train it, you see that there's a considerable improvement. It actually, after about certain epochs, it reaches 100% training accuracy and 91% test accuracy. So you can compare desired specifications and what we actually get, which are very similar. This is encouraging. It means that even this stupid system can learn this particular problem pretty well. And I think at this point I can summarize.
But before you do that,
Yes.
examples, like what are the crosses, what are blue crosses?
These crosses,
Yeah.
these are mistakes. So the circles and diamonds are correct specifications, the crosses are mistakes. So if you compare, for example, this cross, you see that here in the own proof is orange. That's why I marked it as a cross. But the test accuracy here is 91%. And this is not a particularly optimized sheet for one thing. It just works. So it made us very happy. And it tells us in some sense learning is maybe much easier than what we think. All right, so both design and learning change the parameters of the system, but in learning you do this as a result, as a response to examples, and you get this cycle that I talked about. Now we can train machines or make them learn with both supervised and unsupervised methods, so it shares a lot in common with traditional or the more usual machine learning algorithms. It can learn real data, and it also demonstrates this kind of a learning algorithm demonstrates the same traits, not just the one I showed you, but other traits are also shared between learning algorithms and this sort of system. And we might have very interesting advantages. In particular, I talked about continual learning and the ability to generalize, which are two properties that are very hard to encode into design systems. But let me just take a step back for a minute and think about how learning and physics interact. So for the most part, there are two ways. The first way is that machine learning algorithms are used to analyze physics data. And this happens at all scales for all branches of physics at this point, from particle physics to cosmology. The other way is that physics tools, in particular in statistical mechanics, are used to analyze machine learning algorithms, especially the popular machine learning algorithms like deep networks. And I'd like to argue that we can do something a little bit different. So this is, we can use these ideas from learning to make new kinds of materials and robots have this activity, which is more related to what I talked about today. But the thing that I care most about, I would say, is that we can go to a bit more fundamental level and try to figure out if physics can teach us something about learning. And here are just two ideas that I'd like to finish with. So one of them is symmetry. This is again the MNIST database. And it took a very long time for people to figure out how to make a network and a neural network for which this example is the same as this example. For the longest time, people had to train the network on this example and this example separately to make it understand both of them. But in physics, we often get this kind of symmetry for free. In particular, in the elastic network, there's no distinction between these two sets. This is one particular possible advantage of physical systems. The other one, which might be even more fundamental, is the idea of interpretability. So a major issue with all machine learning algorithms is that the computer might learn something, but we don't understand what it learned. And it's for the most part, very hard to figure out what the machine has actually learned. And what I'd like to argue is that because physical systems are so simple, especially mechanical systems, we use them for millennia, and we have quite a good intuition about what they do. So if we have any chance of trying to figure out what learning is, or what a system learns, we might want to look at the most simple systems that we can think of. And this is the sort of questions that I like to keep looking at in the future. Okay, so how are we doing on time? Just right. These are the people who were instrumental for this work. My collaborators on all of these projects. So for Origami, I'd like to thank Matthew, Alexandra, and Beth. Matthew then made a comeback and helped a great deal on elastic networks. And Chucky and Viraj, who spent a lot of time thinking about how we can make Origami do all kinds of neat stuff. But first and foremost, I'd like to thank this man, Alvin. We arrived at Chicago at about the same time. As I said, I was the first graduate student in the group, and it's been a wonderful ride. So it felt really great because on one hand, he's so focused and motivated, but on the other hand, he let me actually do all kinds of work on all kinds of weird questions that I wanted to. So this was like really, really great. And I don't think any of us could, foresee 3 years ago that we were going to end up working on these things. I'd like to also especially thank Thomas Witten, who I met a huge number of wonderful people in Chicago. But I think we can all agree that Tom is a special kind of wonderful. He's really amazing. He does above and beyond. I wasn't his student, but he's always listens. He always cares about what you talk with him about. He gives really great advice, and he taught me not just how to do physics and how to think about physics, but how to go about doing physics, how to love what you do, and look at the work that you and others do and enjoy it on a whole different level. I'd like to thank my committee members, in particular Wendy and Heinrich, with which I worked closely in my first year in Chicago, doing things that are completely different than what I showed you today. But it was also a great experience because it allowed me to see all kinds of soft metal research here in Chicago, experience all kinds of nice things. And also Professor Salman Sethi, who gave great advice and always available for questions and very helpful. So next, I'd like to thank these people. This saying is often attributed to the Marines, but I, of course, mean the Marine mammals of the fishbowl. So, you know who you guys are. But these were, really gave great atmosphere in the office, and I shared so many cookie breaks and coffee breaks with these people. It was always really fun to work with. Last but not least, I'd like to thank my family, my mother and father. My father was here. So in chronological order, these are the guys. I wouldn't be here without them.
It sounds like a bar mitzvah speech.
Of course, my wife Shachar, who joined me here in Chicago for most of the time, it was really critical for me. Really, I couldn't have done it without help. Studying in state and everything. And our newest recruit, Leah, who's not here today, she joined halfway through. But she also, added another layer of bliss and, happiness that allowed us to do so much more and think about other things too. And I'd like to thank all of you who came out here this morning in this wonderful weather instead of being outside. I thank you all for being here and joining in this celebration of quality science. Thank you very much.
Well, thanks for very thought-provoking and beautiful talk. I'd like to ask you a question which is less about the specific details. I think you kind of got towards the end with it. Your last two slides. There's the following. At some point in your talk, you mentioned that the mechanical network you constructed was a cousin or maybe that's an implementation of the concept, and of course a mechanical one. I would like to ask you, as a pioneer in this line of thinking, what do you see peculiar in trying to do these things with mechanical building blocks as opposed to electronics one, in terms of performance?
Yeah, so
besides the interpretability part at the end, which I thought was very convincing.
So I think there's a really interesting difference between not just mechanical, but all kind of physical learning algorithms compared to the computational ones. Is that in some sense you can think of the traditional computational learning rules as non-local in the system. So in some sense, all of the weights of the network, when you show it an example, weights far away change, not just the weights that have to do with the pixel that you have in mind. This thing, I don't know how to do this in mechanics. So when I showed examples to the origami or to the spring network, it can only change locally. The spring can only change according to the strain that it's in. So it really, in some sense, limits the kind of learning rules that you can use. But it's also an important difference because if you want to understand how physical systems learn, we have to think about these limitations.
Why would mechanics be different, for example, from making a circuit? I mean, nonlinearity clearly is something that mechanics does very well. Is there something more specific?
In mechanics, we are bound to this, to the energy landscape. This is the thing that it's called. So we are bound by the types of models that are afforded by physics. So if if for example, these nonlinear strings could not exist, then there's no issue, there's no reason talking about it. Yeah.
That was great. Brought up all sorts of good questions. So, look, when I think about learning, I also think about forgetting. I think you hinted.
At a certain age, it may-
So you hinted at that little bit, of course, by looking at the limit of how many things that the system can run. Can you talk a bit more generally about that?
So it depends on a lot of things. If you want to think about the time scale of forgetting, for example, then if your learning rule is something that looks like aging, for example, the springs can be stiff over some time scale. This is the time scale that you can retain your memory. And then you can think about, oh, if I wanted to encode one state now and another state a year later, maybe the first one was already dissolved at this point. So this is one issue with forgetting. The other issue has to do with capacity. So you cannot overload the system with states because at some point it just collapses. And the usual mode of collapse is seen also in the Hopfield network, and we get a very similar thing here. It's basically, I'll say a bad word, it's a spin glass condition. This is what happens when you load the memory too much. So basically, instead of getting the states that you like, you get all kinds of chimeras that mean nothing.
I have one question to have the training at the end, where you talked about relatively small systems, but you make the system bigger and bigger and bigger. Do you have to be more careful about how you train each fold, or if you have a certain amount of noise in the system, does that kill it at large system sizes, which wouldn't at small system sizes, or is that robust to it because you have more things to train?
I think in the elastic networks, at least, it seems to be more robust for larger systems, meaning at least the capacity is larger. In many cases, also the attractor area is more robust. I don't know about a general statement on this issue because it's really state of the art also in learning theory. People do tend to use really large networks to learn in practical problems, and there's not really a good understanding why large networks work better. So I don't think I can give a very well motivated answer.
So it was very nice talk. So a lot of what you're describing is sort of static mechanical systems where it increases, where it falls. Could you imagine a dynamical bouquet version of this system where you're driving the different frequencies and asking how is the response? I mean, at least, yeah. I mean, sort of yeah. So could you imagine new phenomena that would come out that way? Or?
I don't know about new phenomena. We really didn't work on dynamics, but I know that some people are interested in training for dynamical responses. So this is something that I might know better how to answer a year from now, because I'm probably going to work about some stuff that looks like that. But right now, I don't really know how to incorporate dynamics into it. Yeah.
So I want to go back to the example you showed where the network figured out that a rotated 4 is still a 4, right? So if I think about this more generally in image recognition, so this is really an issue that you would like your algorithm to understand their different equivalence classes. So there are certain things which when they're rotated, they're still the same. For faces, we're lit differently in different images. So there's this walking effect. And that's a different thing than rotational symmetry. Or like I have landscapes, so sheep grazing on a mountainside, right? But what we'd like to understand is that there's 3 objects, and then there are objects which are kind of continuously distributed and somewhat fractal because it's a mountain. The thing I'm trying to understand is that you made a really good argument for why elastic network on something 5 construction would do the rotational symmetry as well. But it's not obvious that you can do the other equivalent classes. And what we like ideally, I would think, is something that could just flexibly switch between all these different equivalent classes, right? Do you have a vision for how we could go from what you have, which is very impressive, to this?
Yeah, so ideally, to get this symmetry for free, any type of symmetry that you can think of, you need the physics to respect this symmetry.
Right. So do we have this much flexibility with a mechanical network? It would be lovely. If we
That's a good question. I haven't looked at very, special symmetries so far. Just looked at simple things, but I just want it to be the state of the art. Machine learning algorithms do not respect symmetries by their nature. You have to work very hard for them to do so. And if you have this kind of systems, they get us these symmetries for free if the underlying system respects the symmetry. So if the symmetry is very important, it might be worthwhile studying these systems to see how they are.
So like a constraint enhances functionality.
There's only one rotational symmetry built into your mechanical networks, and we just identified. I think at least in the context of the machine learning neural network side, David Miller and somebody with CS have been trying to implement rotational symmetry and thread symmetry in the network.
Right. And it was a very hard work.
Yeah. That's very recent. Yeah, just going to get an application.
Any other questions? Not many.
Thank you.
Thank you.